Welcome to a lesson on logarithm base E. So let's get started. Now, anytime you work with y equals e to the x and you're doing calculus and so on, and you're solving problems involving e to the x, you'll end up having to use log base e. And the reason is fairly simple. As hopefully you remember, anytime you deal with an unknown variable in the index, you end up having to take the log of both sides. So if you are, why is my pen done up? So if you are dealing with y equals e to the x, and let's say you had to solve something like, let's say you had to solve, I don't know, 5,000 equals e to the x, and you have to solve for x. Well, the only way to bring x down is to take the log of both sides, and basically to solve at what base log will you take, you'll end up taking log base e of both sides. And so anytime you work with y equals e to the x, you end up having to work with log base e x as well, which is why we're doing it today. So we'll look at log base e of x and its graph, its relationship with y equals e to the x, and how we can graph transformations of log base e of x. Log base ex is also written as ln x, or the natural log of x. And yeah, just be aware of that, especially on your calculator, because on your calculator, if you look over here, right, you have log and you have ln. Now log is log base e. So this log is log base 10. Log is base 10, and it says over here that 10 over there should remind you. And log ln is log base e. That e over there should help you remember. Just to make sure you understand, if you ever had to do log base 10 of 5 on your calculator, you would use this key, because that's log base 10 implied, and this is log base e implied. Okay, moving on. Logarithms base e are called natural logarithms. This is because the number e occurs all over nature. E to the x governs natural growth, natural decay. So you have log base 2 of x, you can have log base 10 of x, but these are not known as natural logarithms. If someone says to you the natural logarithm of 10, they always mean log base e of 10. Log base e is known as the natural logarithm. It's also mathematically the easiest log to deal with because of the work we've been doing up till now. Doing calculus, differentiating e to the x is very simple. It's just e to the x, and you differentiate any other base, and it gets very confusing very quickly because you need to know the gradient at the point x equals to 0. E to the x, easiest curve to differentiate in all of maths. And so the logarithm function with base e, y equals log e to the x, is called the logarithmic function. So we call this the logarithmic function to distinguish it from all other logarithmic functions. So if someone says the logarithmic function, they always mean log base e. They don't mean log base 2, log base 5, log base 10, none of that. They mean log base e. It's the logarithmic function. Alright, anyway, so the graph of logarithms, y equals e to the x and y equals e log base e of x, are inverse functions. Now, if you remember, inverse functions are simply curves which are reflected on y equals x line. And inverse functions are basically more or less when you swap x and y around. So for example, if you have y equals x squared and you swap y and x around, you have x equals to y squared, then these two are simply reflections in this line. So very roughly, if this is y equals x squared, and I'm just drawing a really rough one, then we're going to reflect this along that dotted line. And so x equals y squared would just be like that. And it's very, very rough. I'm sure there's many mistakes. The point is, it's a reflection along the y equals x line. And so, since y equals e to the x and y equals log base e of x are inverse functions, this means that they're mirrored across the y equals x line. And so, without looking at a too complicated of a diagram at the moment, let's just do a simple diagram. This is y equals e to the x. Okay, log base e is just a mirror of that. See how this is 0, 1, 0, 1. Well, over here is 1, 0. We're going to swap the x and y around. Y equals, it's 1, 0. And log base e of x is just like that. It's a perfect mirror. So if I were to draw a dotted line, you can see these two are mirror reflections along this line, along the y equals x line. They're mirrored, reflected. And notice how there's an asymptote here. There's an asymptote there. Notice how this increases forever. Well, log base e of x also increases forever. And yeah, those are the main features, I guess. Let's have a look at the more mathematically correct diagram, I guess. And yeah, just examine that for a bit. The main important thing is the asymptote, and this point here is 0, 1, 1, 0, and the fact that it increases forever. Let's have a look at in more detail. We know already that the tangent to y equals e to the x at its y-intercept has gradient 1. And this is how we came up with e, if you guys remember. We came up with e because we said, is there an exponential, is there a base, such that the gradient over here, the gradient here, will equal to 1 exactly. And yes, that gradient happened to be e, where e is equal to 2.72 or so, roughly. And that's how we came up with it. So the gradient over here is 1. If you mirror this, log will also, over here, have a gradient of 1. Okay. So I've explained that. Let's have a look at some more features of the curve. The domain is x is more than 0. X will never equal to 0 because there is an asymptote. But for every number more than 0, there is, this curve exists. You can give me any number more than 0, and I'll tell you an equivalent y value. The range is all real y, as you can see. For all values of y, there is an associated value of the curve. And so the range, is going to be all real y. The y-axis x equals 0 is a vertical asymptote to the curve. So this is an asymptote, just as e to the x had an asymptote of the x-axis. This has an asymptote of the y-axis. And as x approaches 0 from the positive side, as you approach this curve, as you approach 0 from the positive side on this curve, the y value gets larger and larger and larger, negative infinity. This goes, it's a larger negative number, okay? And as x increases, as x approaches infinity, if on the other hand you go to the right, then as you can imagine, y will get bigger and bigger and bigger, and y will approach infinity, positive infinity. As x approaches positive infinity, y approaches positive infinity. Now this is interesting. The curve is always concave down. Now I know many students think that concave down must always be like this. We'll do more work on concavity in one of the topics next year, but all you really need to know at the moment is that it's always like this. It just keeps going. That's a limitation of my graphics tablet. I can't go more further up than that. But yeah, so ignore this bit, ignore that bit. Okay, ignore that bit. The point is, this is going to increase forever and ever and ever. So this curve is always concave down, but it keeps increasing. It never turns around and starts coming back down. Never does that, okay? It's always concave down, but increases forever. There's no upper limit. There's no horizontal asymptote up there somewhere, a million, a billion, or whatever. Nope. Keeps increasing forever and ever. Always concave down. Okay, let's have a look. Okay, this is very interesting. combining logs and exponential functions. This is the reason we use logs, log base e, is to cancel out e to the x. Is to bring the power down and cancel out the e, more or less, right? So the rule of thumb is e to the x cancels out log base e, and log base e cancels out e to the x. Let's have a look at what it means. So over here, we have log base e of e to the x. Now, as with any logs, anytime you have a power, you can bring it out the front. And so it'll be there, right? Now, log base e of e, that cancels out. So you have just x left over. And similarly, if you have e log e of x, this just cancels out. You're left with just x. So e to the x cancels out log base e cancels out e to the x. So have a look at this question. Pause the video. See if you can figure out the answer to that. And hopefully you got 10. And because you bring the 10 out to the front, and then log base e of e cancels out, you're left with just 10. Similarly, pause the video, see if you can give that a go. And hopefully you've given it a go. The answer to that is also 10, because e to the log base e cancels out, you're left with just 10. I see a lot of students not know this or forget this very quickly. Make sure you practice and put it into Anki, flashcards, whatever, so you don't forget this. It's very useful. Alright, transforming curves. The usual methods of transforming graphs can be applied to y equals log base e. And to help with that, I have decided to have a look at this very, very quickly. So now we're dealing with log base e. E is 2.72 roughly. And that's what we're going to deal with. You can't put e over here, unfortunately. Anyway, it's log base e. Now, what happens if the coefficient in front of log, what happens if I change that? So that's obviously c. Let's see what happens if I change that c. And we're expecting it to get steeper if c increases more than 1. And as expected, as we increase the value of c, it gets steeper. And if I decrease it, it'll get shallower. And if it gets negative, it will flip. And there we go, it flips upside down. That's no different to having x squared. And if you have 5x squared, it gets steeper. If you have negative x squared, flips upside down. So yeah, fairly similar to the transformations of x squared, x cubed, and all the rest of the graphs we've done. So let's set that back to 1. And then we'll look at something else. Alright, so what about if you replace x with x minus 4? If you replace x with x minus 4, we expect the graph to shift to the right. Let's have a look. So xk, I'm going to set to, let's say, minus 4. Oh, no, actually 4, because it's already minus there. So x minus 4, and as expected, it has shifted to the right. And as you can see, changing this value over here shifts it right and left. You can shift it left, you can shift it right, just from changing that. And if you just add on a +5 or a -2 or whatever, it will shift it up or down. And as you can see, it's shifting up or down. So it's no different to all the other transformations we've done. It'll be good revision. Hopefully it should help you brush up on other graphs as well. And let's go back to our slide. When shifting the graph of logs, be careful of two things. So when you're shifting the graph sideways, what exactly are we shifting? In essence, you have to be careful with this graph that you shift two main things. First of all, you want to shift this point. This point is 1, 0. When you shift to right or left, make sure you shift that point, and you have to be shifting the asymptote. Okay, so you shift the asymptote. So if you wanted to shift this curve to the right, first thing you would shift is you would shift the point, then you would graph in the asymptote, and then you just draw a generic line like that. More or less. Hopefully that makes sense. And yeah, so you shift the point and you shift the asymptote. So the homework is as listed on the board. Give it a go, and as always, you can ask me for help on Slack as needed. Best of luck.